So, now we are going to discuss integration. So, let us recall in our school days how we have defined integration. So, for that let us just recall, I will call something called antiderivative. A function f is said to be antiderivative of another function f on an interval I if f prime of x is equal to f of x for all x belongs to I. As you can see that for all practical purposes, we are tacitly assuming that our integral is an open interval and f prime of x, capital F prime x is equal to f of x for all x. So, now we know that derivative of constant function on an interval is always 0. So, if f is an of f, then f of x plus c on I also of f on I for a constant c, because if I take f capital F of x plus c, take its derivative, then this is going to be f prime of x, and we are assuming that capital F is an antiderivative of f. So, this is again f plus c, f x plus c prime is equal to small f of x. So, this is the most general form of the antiderivative. So, in school if f is an antiderivative of f loosely, then what we have defined, f of x is equal to, we introduce this symbol f of x plus c. That was what the integration was taught to us in our school days. So, what we are going to discuss now is that integration as an area. So, let us consider the area problem. Suppose I have, this is my A, this is my B, and this is f of x. Now, I want to calculate the area of this region. So, how I am going to calculate the area? What we know from at a very early stage, that how to compute the area of rectangles. So, let us try to use our knowledge to find the area of this region. Now, let me divide this AB. This is x1, let us say this is x2, this is x3. I am not putting any restriction on x. So, suppose this is sum, this b x n minus 1 and this b is equal to x n. Okay. So, then I join like this. So, what I can do is that I can suppose this is I can find the area of this rectangle, and again we can compute the area of this rectangle, area of this rectangle. Similarly, now, so all these rectangles, if I compute the areas and if I take the sum of this area of this rectangle, definitely the total sum of this area is going to be a bigger quantity than the area under the curve, what we are trying to region, what we are interested to find the area. Now, I make the smaller partitions. So, now in this case, so I calculate the area under this green. I compute this all these smaller areas of the smaller rectangles. Like this. As you can see that if we take the sum of all these green shaded rectangles, then this is going to be the total sum is going to be less than the total sum of the areas of the rectangle we have calculated in the orange rectangles. However, still this green sum of the areas of the green rectangles will be more than the area of the region we are interested in. Now, we go finer and finer, we can do that. I will divide A B into smaller and smaller parts and keep on doing repeat this process. So, intuitively what do you think? This is going to all the sum of these rectangles with the finer and finer partition, they are going to approximate the area of the region what we are interested in. Now, in the similar one, what we can actually do with the same curve, this area if I want to calculate, then I divide A B, and what I do is that in this I will consider this rectangle. like this. So, now if I take the area of this rectangle and take the sum of these rectangles, then as you can see that this total area of the sum of these rectangles are going to be less than the area of the region what we are interested in. Now, if we make the division of A B into smaller and smaller parts, then we will still get the sum of this area of the rectangles to be less than the region area of the region, but it will be much better than the previous one. So, through this process, by taking finally infinitely small length of this, we are going to get the area, approximate the area by calculating the area of rectangles. So, let us formally write it down what we are discussing now. So, now what we have, let A B be the given interval. And we have a function from A B to R bounded. These two things are given to us. Okay. So, now consider a partition P of A B. What do I mean by that? That is, P is a set which consists of x naught, x 1. This is a finite set which is contained in A B such that x naught is equal to A, which is less than x 1, less than x 2, less than x n minus 1, less than x n, which is equal to B. That means, I have A here, B here, this is our x naught, this is our x n, and this is x 1, this is x 2, this is x 3, like this. So, now here if we look at in this partition for this orange or for the green, we are considering the rectangle on, suppose let us look at on the first rectangle, here we are considering the area. So, now what is this? This is f of, in this is f of x 1, this is what it is coming out to be. Now, that means suppose I have a partition and in which we are considering for the yellow one, orange one, this rectangle. Now, what is this rectangle we are considering for the orange and green? So, we are considering the maximum value what f is going to take in this interval x 1 to x I plus 1. So, denote m I is equal to, we have defined the supremum f is a bounded function. So, therefore, there is a least upper bound f of x such that x belongs to and for the yellow one, for this what we are considering the minimum value of f. So, that is infimum of now then what we are doing? We were doing, now we are taking this area of this rectangle, the each area of this rectangle is m I times the length of the rectangle, that is x I minus x I minus 1, then we take the sum of these rectangles. So, we denote P of f, this is equal to x I minus of 1. So, for each rectangle in the yellow or green, this is the area. Now, we are taking the sum, which that means we are getting the sum of all these rectangle, call it that U P f. Now, it depends on what particular partition we are choosing. Similarly, for the yellow one, we have L P of f, which is equal to summation over I from 1 to n m I of x I minus of x I minus of 1. For each I, m I, so in this case, so this is the area of m I, suppose this is x I minus 1 to x I, then this is the little m I into x I minus x I minus of 1. So, we will call this as the upper Riemann sum for partition P, and this we will call the lower Riemann sum for partition P. Now, as you can see that given any partition, P, LPF is greater or is equal to summation over I from 1 to n m I of x I minus x I minus of 1. X I minus x I minus 1 is positive, and this small m I is the infimum of f x in that interval. Therefore, definitely this is going to be m I is the infimum is less or equal to x is in x I and x I minus 1 into x I, and f is bounded. Therefore, so m is, there exists small n and capital M less or equal to f of x is less or equal to m for all x belongs to A B. So, now obviously, all these m i's, they are the infimum of f in a restricted region in the interval x I minus 1 to x I. So, this m, which is the lower bound for f, is definitely greater or equal to m I. So, this we can write that summation over I from 1 to n, the small m of x I minus of x I minus of 1, because x, this is a positive quantity x I minus x I minus of 1. So, which is equal to m summation over I from 1 to n m of x I minus of x I minus of 1. So, this if we start I equal to 1, then this is x 1 minus x 0 plus x 2 minus of x 1 this goes up to x n minus of x n minus of 1. Now, this is a telescopic sum. So, this gets cancelled, x 2 with a minus x 2. So, what you are going to get is that x n minus of x naught, but what is your x n? This is nothing but b minus of a. Similarly, each m I is less or equal to this m. So, you can get that u p of f, this is less or equal to m times b minus of a. So, what do we get? We get m of b minus of a is less or equal to L p of f. L p of f is always less or equal to E p f, because on x I minus 1 to x I, for LPF we are considering the minimum value of f, and for UPF we are considering the maximum value of f. So, this is UP of f, which is less or equal to m of b minus of a. This is what we observe very easily. Okay. This is true for any partition. Does not matter how small things you are taking in the partition. So, now what we define is, so as you can see that UPF and LPF, they are basically the bounded for every p, and they are real numbers which are bounded for every p. So, that suggests us to define a to b f of x dx. This is what we call the upper Riemann integral. This is equal to, because we want to approximate from above, it is the infimum of u p of f. This is infimum taken over all the partition p. You consider every partition p, then you take the infimum value of that. That what you denote it, the infimum is definitely going to exist, and that what you are denoting it by the upper Riemann integral, and you denote lower Riemann integral to be, because for the LPF you are approximating, trying to approximate from below. So, this is supremum, is taken over all p of L p of f. Now, we define f from a b to R bounded. We say that f is Riemann integrable if in upper Riemann integral is equal to lower Riemann integral. That is when we will say that this is Riemann integrable, f is Riemann integrable. So, obviously, and in this case we denote the integration of f, which is equal to so this is what is the definition of the Riemann integration. So, obviously, we would like to see that this definition what we are giving, this has to be the same definition what we have learned in our school days in terms of antiderivative. So, before that, let us try to see that what are let us compute some Riemann integration of some easy function in through this definition. So, example, you take, let f of x is equal to 1 on 0 1, this is just the constant function. Now, we need to, in order to get that, let take P be a partition. Let us say this is x 0, x 1, x n, which is equal to b. Consider this partition, any partition for that matter. Now, we are interested in mi, capital Mi and small mi. Now, capital Mi is going to be what? This is the supremum of maximum of f of x when x is in x I minus 1 to x I. Here f of x is equal to constant 1. Therefore, this is going to be 1 for all I. Similarly, this is, because this is a constant function, this is also 1 for all I. Therefore, UPF is equal to summation over I from 1 to n 1 into x I minus of x I minus of 1, which is equal to what we have seen earlier is 1 minus 0 b minus of a if it is the integral is b, interval is a b, which is equal to 1. Now, LPF, which is equal to this small mi is also 1, this is the same thing, which is equal to 1. Therefore, the constant function is integrable, and the integral by a notation of integral from 0 to 1 f of x dx, in this case it is going to be equal to 1. Now, consider this function, let f of x is equal to 1 on if x belongs to 0 1 minus, let us say, half, and which is equal to 0 if x is equal to half. Okay. So, then what we have got, you see, take a partition, f is a bounded function on the interval. So, we are in the setting of finding the Riemann integration. We need to see that upper Riemann integral should be equal to the lower Riemann integral. So, we must calculate that. Take a partition P. So, in any particular partition, this half is going to remain in one of the subinterval or at most the two subintervals, adjacent subintervals, that is what it is going to happen. Now, we need to calculate mi. Now, wherever this half is does not matter, but there will be other points in that subinterval in which f of x is going to take the value 1. So, therefore, the maximum in that subinterval is going to be 1 always. So, this is equal to 1 for all I. Now, let us compute mi, small mi, that is the. So, now suppose there can be two cases. So, half can be something like, half would be somewhere here, or half can be the end point of this, either this end point or this end point. So, if half is here, then we need to only consider one interval, subinterval, and if half is at the end point, then we may have to consider two subinterval. Mi, suppose half belongs to x I naught minus 1 to x I naught, this is on the open interval. Then mi is equal to 0 if I equal to I naught minus of 1 x I naught, and is equal to 1 if I is not equal to I naught. So, in this particular case, what do you get? You get L P of f, this is equal to total interval will be b minus of a minus of x I naught minus of x I naught minus 1, because this is 1 in other one, and then we have this added term half of, which is equal to b minus of a minus of half of x I naught minus of x I naught minus of 1. So, similarly, if half is equal to some x I naught, then you need to consider two subintervals. Then in this case what you are going to get is that L p of f, this is equal to b minus of a minus half of x I naught plus 1 minus of x I naught minus of 1. So, now the partition is in our hand, right. So, we can choose p for every epsilon positive. We can choose p such that x I minus x I minus of 1 is less than, let us say, 2 epsilon. So, therefore, so what do you get, that L p of f is greater or equal to b minus of a minus of epsilon. This is true for every epsilon. So, L p of f is greater or equal to b minus of a for so, what do we get? We get that b minus, so L, in this case this is equal to u p of f, thus f is Riemann integrable and this is 0 to 1 of this particular f is going to be equal to 1. So, what we have seen is that even we have a problem at some one point. First we considered f of x equal to 1 and then we changed at one point. This definition of this Riemann integral is not respecting any change in one single point. Okay, so, now this would be interesting to see that not every bounded function is it Riemann integrable. Now, for example, consider f of x is equal to 1 if x belongs to a rational in 0 1 and 0 if x belongs to x is not rational intersection 0 1. This is a function we have defined from 0 1 to r. So, now this is a bounded function. Now, you take any partition, this m I is definitely whatever x I minus 1, this m I is always this any interval is going to contain rational. So, this is 1 for every partition and m I, small m I, it is going to contain irrational. So, this is 0. So, therefore, u p of f for any partition, this is going to be 1 and L p of f for any partition p is going to be equal to 0. So, this f, although it is bounded, is not Riemann integrable. So, we will continue with our study of the Riemann integration in the next lecture. Thank you.